Hello YouTube, I'm experimenting with another setup here, so bear with me. So anyway, we solved this problem last week and I mentioned in the comments that my notation was bad. Again, Silent Dreamcast hounds me on notation because notation is important, folks. Even if you get your math all right, if you're not labeling it correctly, it's kind of useless. So here is the proper notation. V out, from what I actually learned recently, is actually in reference to ground. So instead of V out being 2.28, it's actually the voltage drop across here is 2.28. And then V out A is actually V in minus the voltage drop across here, which is 10.97. And as we go around the circle, we get to 0. And I forgot to label ground last time, so my bad. And also the current thing, like, you know, current going like this. Technically, this is like negative I, but when you do all the math, put it on the other side, it goes back to positive I. Anyway, we are going to work on this problem now. And I think last time I forgot to put in the V in, which is 12 volts. And let's focus. Come on, focus. There we go. Okay. So again, we are going to use Ohm's law, and I kind of rewrote KVL just so that it makes sense, because sometimes when you see this, it's like, what is that? It's Vn is equivalent to all the sum of the voltage drops across the resistors in the loop. Okay, so this is a little different from last time because, like I said, the current across here is not gonna equal the current across here. No, they are not the same. So I1 is not equal to I2. Now, do we have to solve for the current? No, we don't. We just have to do what we did last time, but we can't just, you know, take the voltage drop across here and take the voltage drop across here to find out what the voltage drop is across here. No. We are going to have to learn about KCL, Kirchhoff's current law, which states that the sum of all of the currents coming out of the node should equal the current coming into the node. Okay, so these two currents together, added together, should equal this current coming in here. So that's another thing. So what can we do? Can we just take, you know, V in over here and then, no, we can't do that. So what we're gonna have to do is find the equivalent resistance of all of these together, and we'll see why in a minute. So remember that in series you could just add up the resistors together. So then we get something kind of like this. It's just like a super fast, ugly, ghetto thing. We're gonna get something that's 3 plus 1 is 4, 3 plus 5 is 8. So 8.4 K ohms. Yay! Now we need to figure out what 2.2K ohms and 8.4K ohms are in parallel, and we are going to use this little formula, resistors in parallel, and it sometimes is notated like this, but basically the reciprocal of the total resistance equals the reciprocal of the first resistor plus the reciprocal of the second resistor. And if you have more than 2 resistors, you know, you just kind of let me try writing so you guys could see. 1 over R3 plus 1 over R4 and So in this case we only have 2. And then, you know, when you add fractions together, you gotta find the common denominator and all that, and then you end up with this, and then you take the reciprocal of that and you get this. So if I plug in the numbers here, R equals R1, so let's just pick this one as R1. It doesn't matter which one it is at this point. Is 2.2K times 8.4K over 1, no, my bad, over 2.2K plus 8.4K. Now, we do that on the calculator. We have 2.2 times 8.4 over 2.2 plus 8.4. So that's about 1.74. I forgot to put in the K's, so it's 1.74 kilo ohms, right? All right, now we have, let me draw this out. What's a drawing in this one? And sorry, it's a bit sloppy. Forget your grounds. Okay, so there's just 1K, right? Over here, and then this is 1.74K. Now, does this look familiar? Yes, we can totally get the voltage across this resistor at this point here. So what is that? Well, we already established that V out is equal to V in is 12 volts times the resistor that we want to get the voltage across, so that's 1.74 over 1 plus 1.74. Let's do that on the calculator. 12 times 1.74 over 1.74 plus what equals 7.62-ish. Yeah. Great. So are we done here? No. This voltage here is actually the voltage at this point over here. I'll call this Vx. So Vx equals 7.62. Now, how's that going to help us? Well, now we have the voltage coming into R3 and R4. Whoa. Okay, so to put it in simple terms, we can kind of ignore this half of the circuit now and focus on this half. So let's see, our V in we established was 7, sorry. Need to hurry up here, it's 8 minutes already. 7.62 volts. This is 1K, and this is, what is, oh no, actually it's 3.3K. My bad. So it is 3.3K, and this is 5.1K. And if we remember, it's V in. V in is 7.62. Let me label, because labels are important. Over, sorry, R2 at the top, 5.1 over 5.1 plus, what is this, 3.3. I'm kind of shorthanding a lot because, you know, saving time. 7.62 is 5.1 over 5.1 plus 3.3 equals 4.62. Yay, 4.62. So V out, so the voltage drop across this resistor is 4.62. It's also, so remember how I got confused with V out over here and here? It is V out because the voltage coming out here is the same as the voltage drop across here because this node is ground. If I were to do V out over here, it would have actually been, 12 minus the voltage drop across here, which we actually calculated to be 7.62. So hopefully this wasn't too confusing. My next video, guys, will be practical applications of voltage dividers. So I'll be getting like real, actual electrical components and be showing you guys stuff. Okay, I hope you like this video. If you have any questions, comments, or concerns, please let me know in the comments below. Thank you.